Yep.
Yeah.
Hey,
It's more.
just a second.
Hi. Hi, everyone.
So here we are. Thank you very much for joining us in this week of Introduction to Science of University of Nebrija. So let me first of all introduce you to Mr. Giacomo Cerre, that is working for NASA now. Just a very brief curriculum from him. He made his degree in mechanical engineering and was working for more than 2 years in non-linear spectrometry European lab or something similar in Florence, Italy. And after that, he's been working in Mainz, in Germany, where you got the doctorate in inorganic chemistry. Just working about metallic oxides and ceramics for thermoelectricity of high temperature. And now he's joined to the NASA, to the Jet Propulsion Laboratory in Pasadena, California. So I think that his background and his present work are very suitable to let us know what can we expect from thermoelectricity, this technology that we are meeting this week, we are working with, just oriented to the energy recovery and so on. But Giacomo, for sure, can give us a very, very wide and high-tech vision of what can we expect from this technology in a short or medium future. Okay, so the presentation is going to be held in English language. So it is the presentation that Giacomo will share with us. And same way than previous conferences, Giacomo's presentation will be in our system when he finishes. Giacomo, I think you should have presenter powers. So in order to share the presentation with us, are you familiar with this system, or you need guiding?
First of all, I'd like to thank you for the invitation and for the nice introduction. It's a pleasure for me to be here today. I'll try to give you a bit of an overview of what we're doing in a Jet Propulsion Laboratory for Thermoelectricity. I think, let's do it together. I think I will share my screen. I think I will share the screen to be sure the presentation will have the animation working. And yeah, whenever you want me to start, I think I'm ready.
Yes, please, whenever you want.
Okay. Maybe I will switch off the camera for the presentation. I don't know if it's or I don't know.
It's not needed. As far as you begin the sharing of your screen, it will automatically change.
Oh, I see. Okay, can you see the PowerPoint?
We can see that. Yes, thank you.
Okay, let me open the. Now you see the presentation mode, right?
Yes.
Okay. Okay, so again, thank you everyone. As said, I'm gonna present you or like show you what's the work we are doing at JPL on the RTGs. That stands for radioisotope thermoelectric generators. I'm gonna speak about the science, materials, and how important the technology is for the space exploration. This is a picture of JPL in Pasadena. It's not always so great. Most of the year, actually, it's not green at all. It's completely brown because it's extremely dry, and we don't have much snow. But still, so we started the JPL started in the mid 1930s when some college students used this location to set rocket experiments. In 1943, von Karman, Malina, and Persson and Foreman, that are the founders of the JPL, started this Aerojet Corporation to manufacture rockets. It's kind of what nowadays we would call a startup. In November of the same year, it changed its name from Aerojet Corporation to Jet Propulsion Laboratory and became an Army facility operated by the university, by Caltech. So why these people decided to move there in that time was a kind of remote location because there were not many buildings around. So that happened because when they were starting some experiments on rocket fuel in Pasadena, these guys blew up 3 labs, and at that point the university told them, okay, you need to find a new location to do these experiments. And that's why the JPL is located where it is now. In December 1958, JPL transferred to NASA and became the agency's primarily planetary spacecraft center. So basically, most of the vast majority of spacecraft and robotics that it's used in NASA missions is conceptualized, developed, built, and tested all at JPL. Nowadays, we have approximately 7,000 employees on a 177 acres facility with an annual budget of about 2.5 billion. These are the JPL currently active mission. There are 45 of them. Some examples are, let me see if I can show you with the... Okay, you should see the pointer now. So some of them are generally known. They're the Mars Science Laboratory or the Mars Curiosity lander that landed on Mars in 2012. Then there's InSight, is another a lander that want to study the interior of Mars. It landed in November 2018. There are Voyager 1 and Voyager 2 that are 2 spectacular missions. They have been launched in 1977. They're both powered by thermoelectric generators. And they're basically hanging out in space since then. Voyager 1 enter the interstellar space, so enter the region where the gravity from Sun is not relevant anymore. So basically, it exited the solar system in 2012, while Voyager achieved that in November 2018. Nowadays, Voyager is the most distant human-made object in the universe, and this is something totally amazing, especially so you can already start like feeling how really important is thermoelectric technology for space. There are also like a lot of there's a huge fleet of airplanes that are the main purpose from these missions is to study the atmosphere, the impact of pollutants and global warming on our planet. There are a lot of satellites. There's one very nice, it's called Marco. has been launched together with Insight in 2018, and has been developed is a completely new concept of ultra compact communication CubeSat. So the whole satellite, this whole satellite, which is responsible of enhancing the signal, the transmission signal from the robots on Mars to Earth, it's basically the size of I don't know, a small laptop. And these are all only some example of some of the amazing stuff that we're responsible for. So why thermoelectricity? When we want to investigate and do science in the solar system or generally in the universe, the more we get away from the sun, lower is gonna be the irradiance, and for the whole exploration, there are mainly three technology available for powering a spacecraft. The first is the solar system, the solar power, but solar panel have the limitation that they need sun. So if the irradiance is not enough, or you are in the shade cone of some planets, so when they are in the revolution, there are parts that, for example, here mark mainly red, or at least like half of the trajectory around the same planet is going to be in shade, so will not receive sunlight. And as I was saying, the further we get from the sun, lower is its radiance, and therefore to be able to produce the same power output, you're going to need bigger and bigger solar panels. And this is a very complicated development for the solar panel, because the bigger is the solar panel, bigger is the weight that then the spacecraft need to carry, and therefore it's always related to like the economy of the spacecraft, because higher is going to be the weight, higher is the amount the fuel, propellant, and the energy that you need to even just to leave Earth, and that's going to be a big lean on the economy of the mission. Batteries batteries have the limitation of the short lifetime. When we need to do science, especially in the deepest part of the solar system, we need years just to get to the point where we want to do science. And if we arrive there and our battery and our power system is dead, at that point is not really very useful. So in all these situations, thermoelectrics turns to be like an extremely important technology for powering spacecraft. So since the 1961, which is the year of the first RTG used on a US mission in space, there have been 46 RTGs that has been used successfully on 27 missions. As you can see here from the numbers, there have been like 10 Earth orbit mission, 8 planetary missions. Probably most of them, like Pioneer, Voyager, Cassini. That's a lot of really important missions that allowed us to discoveries and learn a lot about our solar system and the universe in general. There have been like 6 of the lunar surface missions. So for example, when they landed in the moon, they carry with them like a small RTG to power some of the electronics they had, and also to control the environmental temperature. And then there have been 3 on Mars surface mission, the Viking 1 and 2, and the Curiosity rover. And now, starting from next year, there's going to be another one, because it's going to be Mars 2020. So this is a bit of the history of the evolution of the RTG. So we started with in the former times with some very innovative for the time generators. The Snap 19, for example, has been used in the Pioneer 1011 on the Viking 1, Viking 2 missions. The Snap 27 RTG, you can see here, this is actually a picture of the moon from the moon landing, and this is a generator I was telling you before has been carried with the astronauts. Then we moved to a multi-100 watt RTG for power the missions Voyager 1 and Voyager 2. We transitioned then to different different system of thermoelectric materials with the GPHS, that stands for General Purpose Heat Source RTG. And then I'm gonna explain you later what's that, because we are still using the same technology for producing the heat that then is transformed in electricity. And what it's the present one is MMRTG, that stands for Multi-Mission Radioisotope Thermoelectric Generator. As you can see, the shape resembles a lot the one of the Snap, and instead it's except for the design has been used that the same design of the Snap, but then the technology inside for the material is completely different. And as you can see here from the table, most of the material that has been used over the time since 1961 until the 2011 are a mix of lead telluride and silicon germanium based material. This is the MMRTG. This is a picture from Curiosity. It's a selfie from Curiosity on Mars. You can see that in the tail of the rover is where the generator is located. And this is a scheme and an exploded vision of the visualization of the generator. So in the center here, it's where the GPHS, a general purpose heat source, are located. There are like 8 pallets of plutonium dioxide, the isotope 238. The natural decay of this material generates, and on the hot side, it's able to generate heat, and that guarantees on the hot side of the thermoelectric module a temperature of about 1373 K, like 1100 Celsius. The cold side of the thermoelectric is kept as a temperature of about 473 K. You can see here there's these are the channels of the cooling system, and then the residual heat it's dispersed towards the external atmosphere through these radiating fins. And here you can see this is the thermoelectric module that then is encapsulated and put it directly in contact with this Higgs exchanger, and so this is where the magic happens. So thermoelectricity, it's a very important technology for space missions. That's for sure, but it's not the only application in which this technology is used. You probably already know over like yesterday from previous presentation, other amazing application for these materials. I'm just gonna give you like a brief overview. Thermoelectricity is used for powering autonomous remote power devices. For example, there's in locations where it's really hard to that are really hard to reach. Thermoelectricity could be a very good technology to be implemented, because it requires a really low maintenance, sometimes not even require maintenance, and it can perform at a very high conversion, very high So it's a very reliable technology and can remain reliable for a really extended amount of time, way longer than solar panels and batteries. There are also some companies that started commercializing some camping gears using thermoelectric modules. For example, you can see here the company Camplight. They use a burner underneath the burner, close to the flames. There's a thermoelectric module that then it's used to generate power or electricity that can be used to charge your cell phone or your tablet or some small electronic devices. Another really important part is waste heat recovery and energy harvesting. According to a study of the Lawrence Livermore Laboratory, only US about 60% of the energy produced each year it's wasted as heat. So if we could convert or like reuse at least even a portion of that otherwise lost energy, would mean really a lot. It would be able to improve the efficiencies of certain system and do not inject in the atmosphere very high temperature gases or liquids, and then we will have also the positive part of being able of producing more energy from something that otherwise we would lose. In sensing, it's and in laser, in detectors, in sensor, it's very used technology. In some case for producing energy, but the most used application of thermoelectricity in sensor is the cooling. It's especially used in laser for cooling down the laser source. Another small applications, but really interesting, are like small scale refrigerator, for example. Also the car refrigerators that are powered through the cigarette lighter. Generally use thermoelectric technology. The active heating or cooling of the car seats is generally done through thermoelectricity, and in a lot of heating elements, the small regulator for the temperature, it's using thermoelectric technologies. So this is a schematic view of what a thermoelectric module look like. It's formed by several P and N junctions that are electrically connected in series and thermally in parallel. Thermoelectricity works mainly through two effects. On one side, we have the Seebeck effect, which is used in thermoelectric generation. In this case, when we apply a temperature difference at the p-n junction, that induce a migration of the charge carrier, that are electrons on the n side and holes on the p side, from the hot side to the cold side, and that generates a voltage. The voltage then is proportional to the Seebeck coefficient of the materials and the delta T, the difference in temperature between the hot and the cold side. The other effect, which is mainly used, I was saying before, for the cooling, it's a Peltier effect. In this case, we apply current to the p-n junction, and that current generates again a migration of the charge carriers from the top to the bottom, and therefore cooling down the top surfaces, so removing heat from that surface and then dissipating the heat on the other side. In this case, a heat flux which is removed from the top surface is proportional to the Seebeck coefficient, the temperature, and the electric current which is applied to the junction. And then the Seebeck coefficient times the temperature, it's also defined as P, so the Peltier coefficient. So the Seebeck effect then is what we use when we want to generate power. Thermoelectric power generator, it's using this equation for the efficiency. You can see that the first term is the Carnot efficiency. I'm sorry for the noise. And the second term is it's the term which is linked to the thermoelectric materials. We have the ZT, which is the figure of merit, which is a function dimensionless parameter, which is function only of the thermoelectric materials that they use. It's the product of the Seebeck effect, the Seebeck coefficient square times the temperature over the electrical resistivity and the thermal conductivity. Now, the goal of NASA for the new generation of thermoelectric materials, or in general devices, is to reach a conversion efficiencies of about 20%. That 20% means that if we are, so higher is the temperature, lower we need to have the average ZT, which is this term here. It's the average ZT, so it's the average value of ZT over the temperature range we are considering. So if we need to improve the conversion efficiencies, what we can do is increase the temperature difference between the hot and the cold side, but that might also impact negatively the average ZT, or somehow we need to improve the average ZT. And to improve the average ZT, we know that we need to act on the thermoelectric materials. The state of practice materials nowadays have an average ZT, sorry, not nowadays, the average ZT of the state materials, so what it's used for in the previous technologies of RTGs is about 0.5. The state-of-the-art materials, that's nowadays of about 1.1 in average ZT, and the best state-of-art materials can achieve a peak ZT, so maximum ZT of about 1.5 to 2. But if we consider how all these parameters are strictly interconnected among each other, we realize it's not really such a straightforward task optimizing ZT, because we can see that in function of the carrier concentration, if we, for example, reduce the charge carrier concentration, we will have an increase in the Seebeck, but at the same time, and the reduction in the thermal conductivity, which is positive, but at the same time, we will also increase electrical resistivity. So we need to find the balance, tuning these all these properties to be able to find the maximum. So the main challenge for material scientists like myself, to improve the ZT of thermoelectric materials, is to being able to decouple the two contribution. On one side, the electronic contribution with Seebeck and the electrical resistivity, and the other side, the thermal transport with the thermal conductivity, in order to achieve what has been defined a phonon glass electron crystals material. So a material that it's a very poor thermal conductor like a glass, but at the same time is a extremely good carriers of or like conductor of electricity like in a crystal. So just to give you a brief overview of the main equations that are used, and like to also dig a bit more on on the relations among all the terms that concur to the definition of the ZT, you can see that I was saying the electronic transport and thermal transport. On the electronic transport, there sigma is electrical conductivity, which is the reciprocal of the resistivity, and it's a function of the charge carrier concentration and the charge carrier mobility. And then this one then can be rewritten as the relaxation time over the effective mass of the charge carrier. But then we can see that so to get better electronic properties, at least electrical conductivity, what we need to have is high charge carrier, but that need to have like a low mass. But that's exactly the opposite we need to have a high Seebeck coefficient. On the other side, we have the thermal conductivity, which is the sum of the electronic part and the lattice part. The electronic part is stands for that part of heat which is carried by electrons and holes. And through the Boltzmann equation, we can see that KL is a function of the Lorentz number, the electrical conductivity, and the temperature. So we can see already from here that if we have high electrical conductivity, which is a positive thing for the electronic transport, that will mean we will have a higher thermal conductivity, which is a bad thing for ZT. Then there's a lattice, which is relative only to it's that part of heat which is carried through phonons that are vibration of the crystal lattice of the material. So it's just dependent on the crystal structure of the material, and it's a function of the heat capacity, the phonon velocity, and the phonon mean free path. So the state-of-the-art materials for the past 50 years, as I said, has been mainly lead telluride or silicon germanium-based material. They had an extremely high level of reliability, long life, but the efficiencies were pretty low because we're talking about a top of 6.5% efficiency at the system level. We have increasing demand of power, so we need higher conversions efficiencies for the RTG. That means higher specific power is needed for more demanding space scientific payloads, and there's also the limitation of the production of the heat source, so the plutonium dioxide, because the process is really expensive and requires a really long time to produce the necessary amount for an RTG. Therefore, what we need to do is to develop advanced or more advanced thermoelectric materials. We basically use two main approach to improve the thermoelectric material performances. The first approach is to start with materials that have complex crystal structures. So the complex crystal structure ensures low thermal conductivity of the material. So we have materials with really, so the unit cell is formed by a lot of atoms. You have really weird disposition of atoms. So these are all parameters that guarantees low thermal conductivity. And then from that, we start improving the electronic properties through some strategies like doping or compositing. Then we will see further on. The challenge is it's hard to control in a precise way the stoichiometry, and also to scale up the production. And we need also to have a theoretical guidance to predict what the structure, what the properties of the structures will be. The second one, we start from materials that are already known good semiconductors. So we start from materials that have already really good electronic properties. And the optimization path is focus on the reduction of the thermal conductivity, introducing nano features. So as I was saying, also compositing or inducing defects in the material. But here also it's hard to have a precise control over the size distribution and composition of the inclusion we want to put inside, especially if we consider that these materials during their lifetime they're constantly exposed to temperatures above the 1,000 degrees C. And also at this temperature, it might be hard to retain the nanoscale features and avoid that this inclusion grows in size. Therefore, for the improvement of the electronic properties, can go for the structural design. So we can look or try to design complex crystal structure that has maybe different layers, where each layer is responsible for a different thing. So, for example, in this case, for the sodium cobalt oxide, we have these layers that are really nicely formed, where the electrical conductivity is really high, therefore they boost the electrical conductivity. But then we have in between these big atoms that are connected to the other layers with weak bonds that are called van der Waals bonding. And these weak bonds and the fact that we have these layers is what generates active phonon scattering centers, and therefore reduce the thermal conductivity. Other ways to improve the electronic properties, I was saying there's doping and alloying. So we partially substitute some of the elements that form the material with other elements that have different properties and different electron count, and in this way we can control the bands, the electronic bands of the material. For the thermal property, doping alloying is also a strategy, because if we choose, for example, if you replace an atom with another atom that is bigger or smaller, or has a higher or lower electronegativity, that will change the nature of the bond between one atom and the other, and the length of this bond. And these are all parameters that affect the thermal conductivity. And as I was saying, the changes in mass also generates defects and therefore scatter phonons. And another important strategy is the nanostructuring. So including features that has nanometer scale sizes that are used to scatter phonons. So this is an overview of what we have at JPL in the lab as a facility. We have a lab where we're doing all the preparation of material. We start from raw materials. We prepare material mixtures. We do the synthesis of them. We press them. We generate then discs and pallets that are used for the characterization. We characterize electronic, the thermal, the mechanical properties of the material that need to be all consistent over time. After that, we have the components and device lab, where we have brazing furnaces, diffusion bonders, we have dicing cells. So once we have these, so what we get as materials from the synthesis and from the synthesis are generally a disc shape, and these discs are cut to obtain the shape we want for the module. Generally are like bar shapes. And then we have also a lab for the high temperature and live testing. for materials. So once we, so both the materials and the modules are then exposed to operating temperature and kept there for a long amount of time, generally months up to a few years. And if instead we want to speed up this process, what you just do, you just increase the temperature. So if you say your operating temperature is about like 1000 C, if there are like all relations that can tell you if you increase or each degree or 5-10 degrees more means for example, like 2 weeks or 1 month more of operation that is guaranteed at the real operating temperature. So I was saying as I was saying, since it takes like a long time to develop generators, so the whole thing from when we start, or like we figure out like new materials, up to when these materials are integrated into a generator, all this process requires years. So we're talking about like 15, 20, 30 years at least. So this is a scheme of how NASA consider a technology ready for being used in space. So each technology is labeled with a TRL number, which is Technology Readiness Level number. Lower is the number, more rudimental and less proven the technology is. What we do, for example, at JPL, we do our fundamental research does. So we study from zero like new materials, and we do the advanced research part. So once we have the materials, we need to scale up the production and start producing the modules, the thermoelectric modules, and start testing the modules and the couples. And all this work can arrive to a TRL level of about 4. After that, we, in collaboration with other industries, we start implementing and upscaling the production of the modules to bring the technology to a level TRL 5. And then there's the last part, which is so we are still involved in this part, but we are not the persons that directly produce it. Here's more like the industries that we basically trained before, along with the DOE that provides all the facilities for building up the generator, and other NASA centers for the production also of the heat source. And they basically implement the whole generator that then when it needs to be put to installed on a robot, if the robot is done at JPL, these generators will be brought back to JPL and installed. So the materials that we're currently studying for future generations of RTGs are, on the N side, lanthanum telluride. It's already known thermoelectric material since the 70s, as characterized by a complex crystal structure, therefore low thermal conductivity, and has good electrical properties that can be manipulated by playing with this X, so pulling out some of the lanthanum atoms from the structure. And it has a peak ZT at 1273 K of about 1.2. On the P-type, work on the ytterbium-14 manganese antimony 11. This is a material that I mainly focused on in the past 2 years. It's an extremely complex structure, so the unit cell has 208 atoms. That it's huge, but the fact that this has all these atoms and these weird features guarantees that have like extremely low thermal conductivity. Is one of the lowest thermal conductivity register for thermoelectric materials. Has a peak ZT of about 1.3 at 1273, and that means it's a 3 times improvement compared to the P-type silicon germanium, which is being previously used on the RTGs. As I was saying, I worked in the past 2 years a lot on these materials, and I'm gonna share with you some of the results of the work that I've done to improve the properties of these materials. So several studies has been done on using doping and alloying in these materials, but has been really hard to improve its properties since basically in the last, I believe, almost 10 years, it's never been improved, the ZT of this material. So we decided to go for a new approach and for composite. So compositing these materials with other materials to generate something that can be better, not only from a thermoelectric point of view, but also from a mechanical point of view, because one of the biggest limitations of these materials is that they're really high temperature ceramics, therefore they're pretty brittle. And so they're fragile, and we need to improve their mechanical stability to reduce the possibility of failure during operation. So a composite, first of all, we need to start from its definition. So a composite material is material which is made from at least 2 constituents that have different physical or chemical properties, that when they are combined produce a new material with the characteristics that are different from each individual component. But another important requisite is that the components need to remain separate and immiscible within the structure. Therefore, we have, you can see here, like A, it's the matrix material, which is the component which is present, so the biggest volume percentage. And then we have B, which is the inclusion or composite material. We have we already know a lot of composite materials that are everyday life use. So we have, for example, concrete, carbon fiber reinforced polymers, wood. Wood, it's a natural occurring composite comprising cellulose fibers and a lignin and hemicellulose matrix. In this picture, we have a black walnut wood. It's a kind of hybrid wood because it's an intermediate between a diffuse porous and a ring porous wood. Another very interesting case of composite is the Swendy structure composite. Is a material that has been developed several years ago from JPL. So basically, this sandwich structure material had the positive aspect of tremendously reduce the volume of the components without affecting much the mechanical properties. These composites fabricated by attaching 2 thin but stiff skins to a very lightweight but thick core that you can see here in the middle. The core material is generally a low strength material, but its higher thickness provides a sandwich composite with a really high bending stiffness and a really low density. Therefore, it's extremely light, but really with really good mechanical properties. So, what did we start? I mean, what I started with the study of composite in the 4111. Idea then was to put inside some metal inclusions to improve the properties of the material. we started doing some research about possible materials that could be used. Nickel seems to be a very good match because has a thermal expansion which is comparable with the one of 4111. The coefficient thermal expansion is an important parameter when we do composite, because if the mismatch of CTE between the matrix and the inclusion material it's high, that might generates internal cracks and bring to the failure of the material, because when the material is exposed at high temperatures, one material expands more, the other less, and then the part where the temperature is lower, one material shrinks faster than the other, and this difference in expansion and contraction can generate cracks in the material. The Young's model is about 200 gigapascal for nickel, pretty good electrical conductivity, but the problem is that it reacted really bad with antimony. Therefore, we couldn't use it. Cobalt has a very similar properties to nickel, and but it has a lower reactivity with antimony. Therefore, we studied the impact of cobalt in the matrix, and so the name of the project I was supervising was called Coconut, or Cobalt Composite Network using Thermoelectrics. I prepared different compositions. I started with 2 volume%, 5 and 10 volume% cobalt. The synthesis of the materials, as I said, we started from raw materials. We do a high energy ball milling, so it's basically a kind of shaker. So we have like this vial. We put inside the elements. We add these balls, and this is like a high-speed shaker. What we obtain are powders are homogeneous, so the elements are homogeneously dispersed inside the powders. We do sintering techniques to obtain then high density pellet that are then used for the characterization of the properties. This, I don't know if you have experience with X-rays or microscopy, but so with these techniques we can understand the quality of the material and figure out if the material is exactly what we are looking for, and we can see that all the materials as being prepared are all exactly what we want. So what we can deduct from here is that the material, it's you can see the signal of the 4111, which is a main phase, and we can see that the cobalt inclusions are pretty well dispersed inside. There's some small agglomeration, but all the inclusions are between the few nanometers and some micrometer sizes. So when then we pass to characterize the materials, we observe that the more cobalt we put inside, the material is more conductive, and that it's as expected. So we have a decrease of the electrical resistivity. The effective medium theory is a theory. It's a mathematical model which is used to predict the properties, especially the electrical resistivity or electrical conductivity and the thermal conductivity of the material. So I try to use this equation to predict what the values of the electrical resistivity should have been, and the surprise, we saw that actually it's more conductive than what this theory, which is largely used, would have predicted. This is also interesting to see when we analyze the charge carrier concentration, the mobility. Cobalt is a ferromagnetic material, has a transition from ferromagnetic to paramagnetic at around 1200 to has this transition. The temperature of transition of cobalt is 1400 K, but what we observe here is that between the 1150, 1200, 1250, depending on the inclusion density, we observe the ferromagnetic to paramagnetic transition that is characterized by this increase in mobility, and then it's decrease and start being constant afterwards. So these let's say reverse U shape of the charge carrier mobility is a very characteristic behavior for this transition for ferromagnetic material. But still, we were surprised that this transition occurred 200 degrees before what should have been happened. And what we explain is that probably due to the tiny sizes of the inclusions and the fact the concentration is so low, the materials so the inclusions, the cobalt act as a single and dispersed, really remote, so they do not communicate with each other, let's say the inclusion from a magnetic point of view, and that reduces the Curie temperature, so the magnetic transition temperature for the material. So as we recall in the equation, generally when you have a reduction of the electrical resistivity, you should have a reduction also of the Seebeck coefficient. But what we observe instead is that the Seebeck coefficient was maintained constant as the same values of the pure 4111, except for the 10% cobalt that showed a very minor decrease. At that point, was to analyze the thermal properties. We can see that for the 2 and 5%, they are still in line with the same value of the pure ytterbium manganese antimony, and instead the 10% it's showed a this increase over the whole temperature range, which is due to the increase of the electronic contribution because it has a better electronic conductivity. Therefore, this is increased, and this parameter it's higher. Also here, I use the same model I used before to compute what should have been the values of the composite material using the equation I showed you before. And also in this case, we can see that the expected values are not really in line with the ones that we measure, and that was surprising. In the end, once we put all these together and we compute the figure of merit ZT, we can see that overall the ZT has been boosted for the 5 volume percent, increase from a value of 1.25 for the pure 4111 to about 1.7 for the 5 volume percent. And this is a very big increase for having just such a low content of cobalt. After that, we saw after showing the results obtained with cobalt, I thought, okay, what about if we use something else? So if we use something different that has a lower electrical resistivity compared to cobalt and has a better Young's model, higher Young's modulus. So this should allow me to have the same effect, so boosting the properties with a smaller amount of inclusions. And that smaller amount of inclusions would probably balance for the mismatch on the coefficient of thermal expansion, because tungsten has a very low CT compared to the one of the matrix material. So in this case, at this point, since I thought, okay, lower inclusions should guarantee the same results, I just analyzed the 2 and the 5 volume percent. The synthesis has been prepared in the same way. So we mix the material, we shake them, we obtain powders, and then we sinter, and we get pellets with high densities that are used for characterization. Also here again, from microscopy and X-ray analysis of the material, we can see that the materials are pure phase. From microscopy, you can see that the tungsten inclusions are well dispersed. And here, if we see the scale bar is 1 micron, so we can see that the inclusions are well into the nanometer size, and we have some features that are a few micrometers big. And the nice thing is that we don't see any cracks propagating from the inclusion into the matrix. So when we have such big CT mismatch, already after synthesis, you would be able to see like cracks and propagating from the inclusion towards the throughout the matrix. What you see here, just like scratching due to the polishing of the surfaces, being the tungsten much harder than in the matrix material. When you polish it, sometimes you pull out some inclusions, and then basically they scratch the surface, which is softer, the surface of the matrix. So here again we can see that, yeah, indeed the 5 volume percent already have like a drastic reduction of the electrical resistivity. Using again the comparison with the theoretical model, we saw that the measure values are way lower than what we should expect for such low inclusion. So this seems to be like a general trend. So it's at least for metallic inclusion in this specific thermoelectric material. Therefore, there's still something that we are not getting right. So the theory which is generally used to predict the properties of the materials, it's definitely missing something. So there's something that is not catching. Surprisingly, with this big reduction of the electrical resistivity, there was no reduction at all of the Seebeck. Seebeck remained constant, and that's a very positive thing for the transfer. But then this tremendous reduction of the electrical resistivity, then we paid that in the thermal. So the thermal conductivity increased, therefore cancel out the positive improvement on the electronic transport, and in the end the ZT remains pretty much the same, because ZT is about 1.3. But then since these materials have higher Young's modulus, and the tungsten is an incredibly stiff material, we wanted to analyze some mechanical properties of the material. So we analyze the hardness of the material. The Vickers hardness, micro hardness test is what we used. You're probably familiar with these techniques, but I still repeat the general theory behind. So we have a diamond indenter. This indenter is brought to contact with the surface, and then a pressure is applied. We investigated loads going from 100 grams to 1 kilogram force. The indentation time was like 10 seconds, so we applied this force for 10 seconds, and we did 5 indentation per each load, and then we took the average value. The number of the Vickers hardness is reported generally like that. So we put first the hardness number, so the values that we obtain here with this equation. Then HV stands for hardness Vickers, so we know that has been done with the Vickers. The difference between the Vickers and the Brinell is the shape of the diamond indenter. In the Vickers, it's square base pyramid. Instead, in the Brinell is a sphere. Then we put the use load in kilograms force and the loading time. If it's this value is reported only if it's different from 10 to or 15 seconds. These are the images from that, and we can see that in the indentation we can see that what actually tungsten is doing is deviating the cracks that start propagating from the indentation. So it's normal to start seeing cracks propagating from there because it's a starting of mechanical failure of the material. But it's really important what actually tungsten is doing. So it's sometimes is deviating the cracks. In some others, it's stopping them before to propagate. So that increase the let's see here, that increase the overall. It's a signal that the material is more mechanically resistant. And indeed, when then we plot the values of the hardness, we saw that at higher loads, there's an increase for the 5 volume %, and that was a proof of the better stiffness of the material. So although the thermoelectric performance did not increase, improved mechanical stability and fracture toughness especially is a very big plus for the integration in a system integration into the generator. So to conclude, I try to show you and convince you how important is RTGs and thermoelectric technology for enabling future and hopefully more challenging NASA exploration mission, especially in the deep space. Modern thermoelectric materials can achieve attractive conversion efficiencies. At this moment, with the materials we are developing, the device level efficiencies are about 15%, and it's a huge increase compared to the what we had before with the silicon germanium couples, where I said it's so the MMRTG arrived to a top performance of about 7.58%, and the silicon germanium was about 6 to 6.5%. The development of efficient thermoelectrics is a material science task for material scientists like me, and it's only the first step towards practical implementation. It's important improving the thermal stability and mechanical robustness through the chemical tuning and the compositing of the materials. Improved ZT and mechanical stability have been attained for the P-type, the ytterbium-14 manganese antimony 11, using the compositing approach in compositing it with cobalt and tungsten. And the achieved results are pretty promising for future implementation in the next generation's RTGs or following generators. These are it's a picture with some of the members of my group at JPL, and with these selfie from Curiosity on Mars. I thank you all for the attention, and I give you space for some questions.
So, Giacomo, thank you really very much.
Thank you.
Which are the last research and steps at NASA about this technology. And perhaps before others make questions, I would like to make you the first one. It looks as if this technology is quite heavy in terms of weight, and we all know that in space technology the weight is something that must be taken with big care. How much or which percentage of the weight of one of these satellites can be the electric generator? I mean, is it an important amount of it?
Yes. So, I mean, for example, if you consider this rover, the percentage of the whole generator, so the weight of the generator compared to the whole mass and weight of the rover, I believe it's in the order. So I think the rover it's about close to half ton or something like that, and the device itself, so the RTG weight is about a bit less than 100 kilograms. So it's a big part of that.
And all that to generate what amount of watts?
So it depends. For the MMRTG, which is what this rover it's bringing on, it at the beginning of life it produces about 120 electric watts.
Mm-hmm. Mm-hmm.
Yeah. So the conversion efficiency of this generator is about like 6%. What we want to implement for the future generation technologies, it's something that would be able to produce about 500 watts.
Okay. So thank you very much. Any other question? You can make the questions in Spanish, as I told you before, because Giacomo speaks very well Spanish. So.
Sí, yo quería hacer una pregunta en español, si se puede.
Sí, dale.
Quería preguntarte a qué temperaturas trabajáis en el espacio y cómo cambian los materiales cuando están en el espacio, fuera de la atmósfera, que hay mucha humedad.
Okay, so I'm gonna probably reply in English because for some terminology, I think it might be easier or like faster at least to reply.
Yeah, don't worry.
For the MMRTG, so these generators and Curiosity carries on, the temperatures are on the hot side is 530 C, and the cold side is 200 C. There have been an implementation or like a proposition for implementing the materials inside this generator to bring the efficiency from 6 to 8%, and the power output at the beginning of life from 110, 120 to 145. And this generator has a different material system. They're called scatterites, and they have on the hot side temperature about 600 Celsius and 200 on the cold side. What instead we are trying to develop now has a high temperature side of about 1,000 to 1,100 Celsius, and the cold side is about always 200 to 300 C. So outside there are different technologies. So the generators operates differently, so for example, the MMRTG is called multi-mission radioisotope thermoelectric generators, and calls multi-mission because it has a possibility of operating in two different environmental conditions. So under vacuum or in Mars atmosphere. On Mars atmosphere, it's really it's not very dense. It's really and the composition of the atmosphere is completely different from what we have on Earth. So it's not a vacuum condition, but it's there's way less oxygen inside. The problem, one aspect that can be problematic for generators, moisture, yes, for sure, but I mean, out in space we don't really have a lot of that. The problem is like evolution of oxygen, because the oxygen might interact with some graphite insulation that we have inside, start generating CO and CO2 that might attack the thermoelectric materials, because a lot of them are really oxygen sensitive, and that might reduce the efficiencies of these materials. But what we try to do, we try to generally encapsulate the modules in a way that there's not much exchange of gas. Even if some oxygen enters the generator, there's not, let's say, the chance for that to react with the materials is extremely low.
Okay, thank you very much. Jordi, you had a question?
Yeah, thank you very much. It's been really interesting. I was my question is around how long, I mean, do you expect the generator to work? I mean, what is the expected lifetime for the? I mean, I guess there's depending on the generator, but as an average.
Yeah. So generally, the missions, each mission is different. Each mission has an expected lifetime. For example, this rover, the Curiosity, was expected to. So the expected lifetime, or like the minimum expected lifetime, was 1 year of mission on Mars. That it landed in 2012. It means we're already like 8 years of missions now. Generally, so far, it never happened that a mission has to end due to the failure of the RTGs. The RTGs always went on providing electric power no matter what. We have missions, so a very good estimate. So we expect the generators generally to work for at least 14 years. But there have been cases, for example, like Voyager is already working. It's still working and still provide a pretty good amount of power after more than 40 years of mission. So if we think about that, it's impressive.
Yeah, it's pretty amazing. Yeah, thank you.
Sure, thanks.
¿Una otra pregunta? Carmen?
Hello. Hi, Giacomo.
Hi.
Nice presentation. Thank you very much. Well, I would like to know, because I'm working on another kind of source that NASA has used sometimes to power some aircraft, like thermoacoustics. I don't know if you know about those technologies, which is classic Stirling engines of the company SunPower, or the thermoacoustic technology of the company Northrop Grumman. I don't know if you know something about that, alternatives to Thermoelectric.
So I don't know in person these companies you mentioned, but yeah, the Stirling is another technology that is developed from NASA in terms of nuclear power production, and it's a completely different concept. So we have why the RTGs are a completely stationary system, so there's no moving parts, and that's also I think one of the important components that confer to the system this really high reliability. Instead, the Stirling has this, it's more like a volumetric motor, so it has this compression and expansion of the chambers, and so it has this motion, continuous motion going on, and that, I believe, generally it's still like subject of worry and like a very delicate part of the whole system. I believe the efficiencies are higher compared to the RTGs, but still RTGs, I think, are a more experimented and a more reliable technology for operating for long times with no needs of maintenance. But definitely, it's the technology that also has been it's under study for NASA.
You say, I have a question concerning this reliability aspect. We are doing some practical exercises with one of these thermal modules of 4 centimeters by 4 centimeters with a lot of small cubic pieces with welded cubes and so on. So in one of these parts, there are more than 200 weldings. And if I want to make a generator of 100 watts, I will need more than 1,000 of these junctions, which is in terms of the architecture of the thermoelectric generator that you develop there. The architecture of the generator is quite similar to the ones we can see at home, or are completely different? Because during the launching, and I can imagine that the vibrations are quite high.
Yeah, you're totally right. There's all these aspects are extremely important when we need to design a generator. So for yeah, there are like several techniques to build up the generators. I cannot disclose like the details of that, but there are like different strategies to build up the modules, welding or others. Overall, for example, for the MMRTG, the total number of couples who produce 110 electric watt, we had to use 768 thermocouples. It's the same for the implementation of that, and then for the future, that might be like a different approach. So if you have more performing material, you will be able to reduce also the number of couples that you need to produce that amount of power. So we are confident that in the future we could reduce the number of couples that are needed to achieve the power output that we want, and that would definitely reduce also the architectural issues for the generator. So less couples, you have, let's say, less worrying or less things to be worried about.
Okay, thank you very much. Any other question? So, Giacomo, thank you really very much. It has been a pleasure to hear you, to try to understand how important this technology is for autumn space, and which are the differences between the thermoelectricity we are using here at home and the ones you are researching there, and how important is thermoelectricity to space industry and space research. So again, thank you very much for your availability, for your comments, and for your information.
Thank you so much. Thanks for giving me the chance to be here with you, share like some of the results. Thank you, Javier, for
of course, when all this problem with the coronavirus it's over, you are kindly invited to visit us here, of course.
Yes.
Will be my pleasure. I will be happy to. Yes.
So thank you really very much, and hope to see you soon.
Thank you so much. Thank you so much for your kind attention, and to the students, good luck with your project.
Thank you.
Thank you very much. Bye.
Bye.
Hasta luego.
Muy bien, hasta luego, hasta mañana a las 9:30 a todos. Muchas gracias.
Gracias por todo. Hasta mañana.
Hasta mañana. Cerramos la grabación. Eso es. Muy bien. Hasta mañana.